35 light-years from Earth, a planet designated L9859d operates in a compact orbit around a red dwarf star. The current scientific assessment of this target points to a specific and highly unusual profile. L9859d appears to be a low-density world defined by a deep, global magma ocean beneath a thick, sulfur-rich atmosphere. Analyzing a target at this distance presents a strict intelligence gap. No probe has visited. No telescope has direct imagery. Every detail relies on intercepted photons. Interpreting a world under these conditions means analysts must treat distant starlight as a complex data payload rather than a simple visual picture. Recent headlines have categorized L9859d as a planet that should not exist. That phrase requires clarification. The target adheres perfectly to the laws of physics. What it violates is our established planetary taxonomy. This diagram outlines the standard intelligence matrix for exoplanets. We rely on strict columns, dense rocky worlds, fluid water worlds, and gas-rich mini-Neptunes. When plotted, L9859d falls outside accepted parameters, hovering in the undefined negative space between known columns. To understand a planet trapped in this anomalous hybrid state, astronomers had to reverse engineer its internal mechanics from the chemical exhaust floating in its atmosphere. The target's operational environment is extreme. It completes an orbital track every 7.5 days around a highly active red dwarf star. We gather data using the transit method. This is an observational technique where a planet passes directly between its host star and our telescopes, providing a brief window to capture information. During this transit, the planet's atmospheric rim acts as a precise chemical filter for the incoming stellar radiation. The core analytical tool used to decode this light is called transmission spectroscopy. This is a technique that measures which specific colors of starlight are absorbed by a planet's air. Looking at this resulting spectrum bar, the physics are highly predictable. Specific gases absorb precise wavelengths, leaving vertical black bands where light drops out. The primary collection asset deployed to intercept this filtered signal is the James Webb Space Telescope. The raw intelligence retrieved by the telescope was a highly specific pattern of missing wavelengths. Once decoded, these signatures provided high-confidence detections of distinct sulfur-bearing compounds, specifically hydrogen sulfide and sulfur dioxide. Identifying sulfur in the upper atmosphere is the initial finding. This chemical presence points toward a hidden thermal engine capable of generating it. Atmospheric sulfur at this extreme volume cannot exist statically. To remain in the atmosphere, it must be continuously replenished. The intercepted sulfur is a massive dynamic exhaust signature. This volume represents a continuous output from the planetary interior. Heavy concentrations of sulfur indicate an active, ongoing exchange between the planet's surface envelope and a massive internal reservoir. A mature planet with a solid rock interior lacks the mechanisms to maintain this volume of volatile outgassing over its entire lifespan. To match the collected data, a specific internal engine is required, a planetary-scale, molten silicate layer extending thousands of kilometers deep. The intercepted atmospheric signal serves as direct evidence of a massive, hidden internal thermal engine. L9859d is billions of years old, placing it well past the expected window for the violent, heated phase of formation. This dual-track timeline illustrates standard evolutionary models. Young, hot rocky planets predictably cool and solidify over time. By contrast, the bottom track shows L9859d deviating from the baseline, apparently stalling out in a half-finished molten state. This stalled state is maintained through a perfectly balanced, stable thermal equilibrium. In the first half of this feedback loop, the dense, sulfur-heavy atmosphere traps both incoming stellar radiation and internal heat, effectively insulating the core. As this flowchart diagrams, the insulated molten interior then continuously outgasses volatile elements. This constant outgassing prevents the atmosphere from depleting, locking the entire planetary system in a sustained cycle. The target operates as an active, self-sustaining thermodynamic machine that directly defies linear planetary aging. Based on these findings, we must reevaluate the target's initial classification as a super-Earth. Categorizing a planet strictly by its physical radius is an inherently flawed metric. Size is not a reliable proxy for a planet's identity or its internal mechanics. Early analysts were restricted by a localized training set, our own solar system. Relying exclusively on Earth, Mars, and Neptune as baseline profiles severely limits our ability to predict novel, stable hybrid states elsewhere in the galaxy. A mature intelligence apparatus must recognize when its baseline models actively prevent it from analyzing anomalous data accurately. This entire structural assessment relies on zero direct imagery of the magma-ocean itself. The model achieves high confidence strictly because it is built from converging, independent data streams rather than a single indicator. Analysts unified the target's specific density metrics, spectral absorption signatures, and calculated thermal dynamics into one cohesive model. L9859d functions as the prototype for an entirely new planetary class. Future search algorithms will be updated to target these specific low-density, sulfur-rich parameters across other star systems. The universe will continually expose the limits of our taxonomy. True discovery requires the discipline to let raw data break the established model.